Welcome everyone. Welcome back to the second session of the SECAI workshop. And our next speaker going to be Sonya. And Sonya is going to speak on one size doesn't fit all, a dynamic heterogeneous learning ensemble for Malware classification. Sonya, it's over to you.
Okay, thank you very much. Do I have?
Unfortunately, no.
Oh, okay. Thank you very much. So I'm Sonya. I'm from Purdue University, completing my PhD. And our work here is in conjunction between Purdue University as well as the University of Southern California and Santa Barbara. The National Science Foundation are one of our primary funders for our work. And I said that. And then also just a quick disclaimer that the views are those of us, the researchers, and myself as the presenter, and don't necessarily represent the United States Department of Defense, the U.S. government, or the United States Air Force. Okay, so if we look at the research problem, in fact, this talk is a very nice follow-on from the talk that Sammy had previously. So on a daily basis, top cyber threat intelligence agencies report the discovery of over 1 million unique malicious samples. However, when we look at these unique malicious files, we can actually see that most of them are not novel, but instead they belong to previously discovered malware families. And so our work here is to understand what are those similarities as well as the differences between malware families in which they share common code bases and capabilities. And then state-of-the-art models as well. I have a clicker, or I'm going to use a laser. Yeah. So state-of-the-art and traditional approaches often use a single model, a homogeneous ensemble, or various classification approaches that we want to improve on that with our heterogeneous classification ensemble. And so here we're saying a key limitation is the inability to consistently classify large, highly diverse real-world data sets that we're addressing in our research effort. So our work, we have three primary contributions. The first one, we develop a more realistic real-world data set that is taken from existing entities. So as soon as a new malware sample or samples related to a malware family are discovered, we're able to analyze those and increase that into our data set. So our data set on GitHub is called Mabel. That's our malware analysis benchmark for artificial intelligence and machine learning. So that's what we're doing in Mabel. And our second primary contribution, we are releasing a heterogeneous ensemble, as well as a classification arbiter that's able to interface with an n number of trained samples. And so that n number of trained models, in order to leverage the strengths of each individual model to increase classification accuracy and precision. And then the last one, we developed an enhanced classification reporting system. And that's because explainability and targeted optimization are important, especially when we're dealing with so many unique models, and thus we're improving that in our research effort. And then our key takeaway, so we kind of developed two separate unique entities in the same research. So one of the primary takeaway is the heterogeneous ensemble that you can apply to various classification domains. So we developed that, and then we apply it to a malware data set that we created in order to assess how well does it perform. Here is our data set pipeline in which we start over here until we get to our final classification disposition. So we start by taking a corpus of known malicious files. We can actually take a corpus of legitimate files as well. And then we created two analysis agents. So we use these analysis agents to understand and extract features and standardize these features from every sample within a various size corpus. And then we produce that into a knowledge base. And so then we have our separate file descriptor agent that interfaces with the knowledge base in order to produce our standardized data sets. So this is important, similar to what Sammy mentioned in the previous presentation, that right now, if we want new updated samples, you often have to wait a while until researchers are able to produce this into some older data set. But with this system, we're able to immediately pivot to a brand new sample, standardize the features, and then directly go into ensemble modeling. Then our next phase, our next research effort is to actually create that heterogeneous ensemble. So our current ensemble consists of 61 trained models on various modalities inside our data set. And then we interface that ensemble with our classification arbiter that's able to understand what is the optimal decision from the ensemble, and then the classification disposition is produced, as well as enhanced reporting to let us see how do we need to enhance our ensemble overall. Now down here is just a very, very small snip of what that data set actually looks like. Right now our data set Naval on GitHub has over 600 unique attributes inside the data set. So those attributes I'm showing the modalities here. And I'll go through that in the following slides. So for one instance, we start with the identifier as well as the label. That's what you see at the beginning. And so the label inside our data set is the family name because we're working on malware family classification for each instance that we receive. Then we do have lots of metadata inside our data set. And again, as the previous presenter mentioned, there are some features that you do want to eliminate, but there are others that would be good for classifying your data set. And so whenever we do standardize, we also do pre-processing to the data set, we keep the values that are good for training our various models, like file size, entropy, and then we also perform a deep inspection of the opcode. So we look at the opcode disassembly of each sample, and then we add summaries as well onto the data set. And that's what we mean by the opcode summaries. And it turns out that these are much better discriminative features than even the metadata that we have. And then we'll see that in the paper as well as our final results. Then we also include import functions. So we include sorted and sequential import functions to allow you to use various models. For instance, transformer models will work well with your sequential data. If you want to use unsupervised learning, you can use the you can use the sorted import functions as well as the strings in order to help you classify different sets to different malware families. Then we also extract capabilities. And so if we do want to see the capability or the behavior of malware samples, we include that into our data set. And lastly, as I mentioned, we include standardized strings. So when I say standardized strings, it just means we kind of want to handle quite a bit of the pre-processing, such that we go through like your natural language processing, kind of a pipeline. So we perform stemming as well as lemmatization on the strings, and we eliminate a lot of noise and superfluous punctuations, such that you can immediately take these tokens, which are still sequential. You can choose to sort it if you like, and then go back into classifying on your various sequential data bundles. Now, if we look into our classification arbiter construction, so I mentioned in this data set, or excuse me, for this research, we actually trained 61 models, unique models on at least 3 modalities that we showed in the data set. So when you have so many different trained models, like the question is how do you interface and get the appropriate prediction out from this from our models? That's the introduction of our classification arbiter. So with our arbiter, we need 2 primary things. Number one, we need our policies, our ensemble arbitration policy. So we create ensemble arbitration policy in order to govern how the arbiter makes decisions, as well as reconcile conflicting recommendations from the ensemble. And then we also need per class evaluation of each model. So the per class evaluation allows the arbiter to know how truthful or how precise or how useful have each model been inside the ensemble during validation in order to say this is the right model that we want to use your prediction for our test as well as deployment. And then in our research right now we have 3 primary ensemble arbitration models, and we quickly named them conservative, electoral, and objective arbitration policies. So our electoral arbitration policy, this one is mainly a hard voting in which you care for consensus from the ensemble in order to provide that final disposition. Our next one is an objective ensemble arbitration. So the objective ensemble arbitration implements dynamic classification selection in which the best single performing model for each instance that's being recommended in our test set, that's the one whose prediction is going to be selected by the arbiter. And lastly, we have our conservative arbitration policy, which is like dynamic ensemble selection. So this selects a subset of models from our entire ensemble, as well as heuristics that we developed that we'll show on this slide, on this slide here in order to make that final disposition. So each of our arbitration policies has a decision flow, and that's what I mentioned. It's a decision flow of how will the arbiter govern decisions for each instance. So in this case, the conservative arbitration policy, this tends to be our best policy for the training that we've done in our models so far. So we start with the best overall performing model, and then the arbiter says this is going to be our initial recommendation. Then we check other performance of our different models in the ensemble to see, are there a single model that performed exceptionally well in our classification, or a grouping of models that we now need to update our decision. And if that is the case, the arbiter is actually able to update its prediction in order to try and find the best prediction for each instance that we're analyzing in our test set. But finally, even though we can train models, let's say our data was insufficient for a particular instance that we want to classify, we still introduce a distrust value. And so the distrust value, this is a separate instance based on the evaluation metric that we're using for all of our models to say this prediction, although this seems to be the best prediction, it's still a highly unreliable prediction. And so we want to be able to identify those. So this is immediately where we either go towards targeted retraining, or it could be an instance of a mislabeled sample, or it could be an instance of a brand new sample that we've not seen before. So we need to identify those. And that's the introduction of our distrust measure that we see here, in order to give us just an additional alerting mechanism inside our entire ensemble. Now, if we go towards our experimental setup. So as I mentioned, in this data set with our Mabel and our analysis, we partitioned the Mabel data set into 3 primary modalities. And so that's looking at our numeric metadata as well as the opcode statistics that we showed at the beginning of the presentation. We have sequential API import functions that we care about, which is good for embedding as well as natural language processing, and we use natural language processing models inside this analysis. And then finally, strings, the same thing. And so we want to see, even though we have various modalities that we're testing, how can we use all of these models in order to enhance our classification accuracy overall. So our heterogeneous ensemble is now trained with 61 models that we used here. It's about 20 models per feature modality right here that we spoke about to build the ensemble. Then, as we go towards our testing, we use stratified threefold cross-validation in our training and our validation set, and then finally our test set. So our training set is 80% of our data that we start with. Our validation is 15%, and we use those to help us kind of tune hyperparameters for our classification arbiter. And then finally, our test, our result, is 5% of the data set. That's randomly selected and excluded from training and validation. This is the number of final samples that we're doing our testing on for results. Now, in our methodology, it is important to select the appropriate evaluation function for the feature modality that you're training your models on. If we're familiar with this type of work, commonly you'd see F1 score as the primary evaluation function that we want to use, or precision, or recall. Sometimes those are the best evaluation functions, but sometimes it's not. Classically, in research, you'll also see it whenever we're working on kind of string-based data. Jacquard index is actually a pretty good evaluation function that we want to use for specific data sets. So the question is, with a heterogeneous ensemble, which is the best evaluation function to use for each trained grouping of models inside your ensemble? Well, in order to help us kind of evaluate consistency of our different functions, we apply mean absolute correlation to all of the evaluation functions. And then we want to see which specific evaluation function is most representative for the data set. And then we broke these into tiers. And so we can actually choose any of the evaluation functions from like tier 1 in order to say, I will use this, supply this to the arbiter. And now the arbiter can use this to measure the usefulness or the generalizability of the models inside the ensemble. Okay. And then we, as I mentioned, we do this for each modality. So our strings, it will have its own mean absolute correlation. Your metadata and opcode, each grouping of models, you will apply this, and then we select the best overall evaluation function for each modality. Now, we move into the results. So inside our results, we benchmark our 3 arbitration policies inside the heterogeneous ensemble to 2 other main instances. So in our previous conversation, we took the model, the hyperparameters trained from the Amber as well as the Bottomless data set that they also looked at malware classification, and Bottomless looked at malware family attribution. So we trained their model, which is what we do consider as one of the state-of-the-art. That's a light gradient boosting machine model. And then we also took CLAMP AV, so a well-known, well-used signature-based antivirus. I wanted to see how well the signature-based AV are consistent. Do signature-based AV as well as one of our known models compare to the results that we are creating here. Then we executed 9 experiments for each of our arbitration policies. And so within each experiment, we increased the number of minimum unique samples per family that we want to classify. So overall, we also wanted to ask the question, is there a minimum number that we need to have inside our test set in order to say, yes, we better trust the results of the model? And then where does this peak? Or do you see like random numbers? But instead, this is nice that at least a minimum of 2 or more samples inside our test set, which correlates to the minimum number of samples inside our training and validation, is more useful in order to help us come up with good results. And then if there are questions, I'd love to talk about it more when we get to our question side. Now, overall, our conservative arbitration policy inside our heterogeneous ensemble, this consistently outperformed our other model arbitration policies, as well as the Ember trains data set, the Ember train model to this data set, and of course ClamAV, which beat the signature-based detection. So if we look further at our results and our numbers, we're trying to show our mean macro F1 score, mean weighted F1 score, as well as our mean micro F1 score. So I mentioned overall our conservative policy within our heterogeneous ensemble. This performs the best across our data set for the models that we train. Then we also see that ClamAV, as well as the light gradient boosting machine model, did not perform well at all inside our Mabel. So on the bottom side, we're showing the true numbers. And so this was the total number of correct classifications as well as incorrect classifications, and the classification or the correct accuracy for our policy that we tested inside the data set. And so just as I mentioned, our heterogeneous ensemble, this achieved strong performance in this data set, which is promising for what we're trying to achieve here. Then our electoral and our objective policies, these performed well, but not as well as our conservative, which again is the balance between consensus as well as single selection models that are providing results or predictions inside our data set. So we're just showing anytime that we choose a strict methodology, strict consensus, or strict single class specialization, these are good in many test sets, but not always. There are benefits of being able to switch, and then including the appropriate heuristics to train the arbiter to make those decisions. And then here we're showing that ClamAV and light in the LGBM model did not perform well on this highly imbalanced data set. Classification reporting. So I also mentioned that explainability and analysis of how well do our models perform, this is important to analyze and view inside our data set. So we create both tabular as well as visual summaries of how each model performs how each model performs to each specific class inside our data set. So overall, we see for each class, we can determine the best models as well as how well do they perform. And then again, when we go back to our distrust threshold, we can see that there are still classes or labels inside the data set that no model is able to perform well. And in this case, we can ask the question, okay, why is that? Perhaps we have mislabeling, or we just need to do targeted model retraining or optimization inside our set. Okay, so just real quick, and then we'll come to conclusion and questions. So we have a case study. So inside this case study, we explain it, I believe we explain it well inside our paper, that there's a specific instance that we want to just understand why does the arbiter make a decision and then change its decision for the correct answer. So here we start with an instance from this Grim plant malware family. The challenge, as I mentioned, there are many different instances and families that share very common similarities and capabilities. So the arbiter's decision, it initially started with what our top performing model, which was a random forest in this data set, which said it's a coadic, the instance belongs to the coadic malware family. Then the arbiter next look at the consensus vote. Okay, what did the majority of the models in the ensemble predict? Majority of the model predicted that that instance belongs to the coadic malware family. However, the final disposition from the arbiter, it selected a Grim plant. And it diverged from what the top model as well as what the ensemble decided in order to arrive at the correct decision. And then something that is interesting is right here. So even though this specific model, logistic regression, even though overall it had one of the worst performances for the entire training, but we can still leverage, with the arbiter, we can still leverage specific strengths of models in order to provide the best response. So I hope I'm explaining that right, that even a poor model at certain times can provide you the best classification predictions, or our arbiter was able to identify that based off of its heuristics and then provide the right disposition. And then in our paper, we explain this more, as well as provide the actual flow of decisions inside the research. How much time do I have? Okay, 3 minutes. Okay, so just real quick, related work. So we did look at the Ember data set a lot, as well as the Bottomless data set. And so they introduced good data sets as well as good trained models, and their models often found or achieved useful results. Ember, this year, 2025, like in June, they just released a new paper with even millions of new samples inside their data set. But one of the interesting things that they reported inside their paper was a macro. Even when they trained their state-of-the-art model, they only achieved a macro F1 score of 0.43 for malware family attribution. So even though our data sets are different, and they have many more samples inside their data set, both of these corroborate the difficulty of malware family attribution, but it does highlight the potential benefit of using heterogeneous classification ensembles. And so we'll be taking that and then in the future seeing how well our model can improve the overall classification performance. So in conclusion, we looked at the problem of malware family classification, and then we provide that contribution of an autonomous framework that's able to help you produce relevant data sets right now. We released the enabled data sets that we spoke about, as well as our heterogeneous ensemble that's able to provide enhanced results for our current data set. And so our broader impact here, this is kind of like the main point to take. So we are focusing on malware family classification, but this ensemble is fully extensible and scalable, as well as domain agnostic. And so that means if there are other classification domains that you want to work on, you can fully port this exact concepts to other areas in order to hopefully increase your precision and generalizability. Okay, that's all the time I have, and I'll take questions first. Thank you for that.
I think we got time for one quick question. Any question? A question from me, a very quick one. And Ensemble model, so usually vulnerable or maybe having a risk of overfitting. For example, take random forest, that can be, so those type of models can be easily overfitted to the training data.
That's correct.
So in your case, you use 61 models, and also you train your model test and your model based on malware data. When we come to malware, again, some malware families may be underrepresented.
Yes.
And also there may be some similarities between different classes as well.
Correct.
So considering all these things, is there a risk of overfitting? Have you investigated?
Oh, that's correct. Yeah, so that's a great question. So in essence, we're looking at the risk of overfitting, in which our models are, like we're learning too much to our training data and not enough to our test set. So with regards to overfitting, that one in particular, I did not specifically investigate. I'll have to go back because when we do look at so when we do look at this, it's although I'm showing lots of green and like well performance of many of our models, most of our models inside the actual training with the real world data set, like it's much lower than our best overall performance. So in those instances, like overfitting was not our challenge in the data set, and that's because it's so imbalanced that some malware families we may only have 5 or 6 unique instances, and so we still break it up with 3 that's going to be trained on, and then the other 2 that's going to test and validation. So I would just say, since our data set was truly so imbalanced, it was hard for us to achieve really high results consistently, like each of these individual models. I'm showing the best ones here because I did want to talk about the different modalities that were used to best predict certain classes, but in general, at least for us, with our real world data set, it was hard to even feel that our models are overfitting because it's such a challenge that no model, in essence, was this good consistently.
Thank you.
Thank you.
Yes,